So now introduce a method which is simpler than the guaranteed method, which is still guaranteed, and it may involve more computations, but it's conceptually simpler. I hope, at least for me, it is conceptually simpler. So let's first go to revisit this example we just saw before, where the quick and dirty method failed. Why did it fail? If you want to remember, we found 4 vectors and they form 2 threads, this one and this one. So how did we find these vectors? We picked a random vector to start with. We tried to find a vector that when we apply n to it, we would get this vector, and we found there is no such a vector. And then we applied n to this vector. We got this one, we applied n again, we got 0. And only 2 vectors, that's not enough. And now we picked another vector from the basis, from the canonical basis. We picked the first vector from the canonical basis that was not in the span of these 2. And that vector, we applied n to it, we got this. We applied n to it, we got 0. And we tried to find, is there any vector that when we apply n to it, we get this one, and there was nothing. And we ended up with these 4 vectors. These 4 vectors here. So 4, we're in a 3-dimensional space, this cannot be a basis, and we just declared the procedure to have failed. But now let's look at this thread. This thread is actually a good material for us to work with. From the point of view now of this algorithm of playing with threads, of stretching and reducing threads. So this here, we cannot stretch these threads anymore than they are already, because they are all closed threads. They end at 0, which is something we call closed threads. I call it closed threads, but we can reduce. How do we reduce? We see that the last vector, which is the tip of the thread, they are linearly dependent. Okay? So what do? We will add a linear combination, which is a multiple. We'll add a multiple of this thread to this thread. Then this thread will become, this vector becomes 4, 15, and 9. This vector becomes 0, so we can write the thread like this. Now we have 2 closed threads, and the tip of these threads is linearly independent, so we're done. We're finished. This cannot be further reduced because it's linearly independent, but we don't want to reduce it. We don't want to stretch it. We got 2 threads, and this gives a Jordan basis. All we have to do now is write this basis like this. This first thread, I put it here. The second thread, I put it here. And we check. We compute what is our matrix or our operator now written with respect to this basis. What basis? This vector, then this vector, then this vector. And here we got our Jordan blocks. Very simple Jordan block. And here's the one. And we could even tell beforehand that this block would have length 2 and this one could have length 1, because the thread here has length 2 and the thread here has length 1. So I hope this illustrates how to apply the simpler method, but I'm going to show now more complicated examples.